Hi everyone. In this lecture, we'll continue to talk about hypothesis testing. In the last lecture, we talked about hypothesis testing in general. We covered all of the vocabulary in hypothesis testing, and we also covered some daily life examples to help us understand the logic of hypothesis testing. In this lecture, we'll go over a specific type of hypothesis test called the two-sample t-test. A two-sample t-test is often used in social science research, and in this lecture, we'll go over all of the details of a two-sample t-test. First, we need to talk about the type of study in which a two-sample t-test would be used. In some types of social science studies, a researcher wants to know whether the mean of one population is different than the mean of another population. For example, a researcher might want to know, is the mean IQ of people who listen to classical music different than the mean IQ of people who don't listen to classical music? A researcher might want to know, is the mean GPA of people who study with distractions different than the mean GPA of people who study without distractions? And a researcher might want to know, is the mean hours slept per night by working college students different than the mean hours slept per night by non-working college students? In each of these three studies, the researcher wants to know, is the mean or average of one population different than the mean or average of another population? The researcher wants to know, are the two population means equal, or are the two population means different? In this type of study, a two-sample t-test is used to reach the conclusion at the end of the study. So each of these three researchers would use a two-sample t-test to decide whether the mean of population 1 is different than the mean of population 2. And at this point, we'll actually we'll talk about the big picture of a study in which a two-sample t-test is used, and we'll start by talking about the type of data that has to be collected in this type of study. If a researcher wants to know whether the mean of one population is different than the mean of another population, a researcher has to take a sample of population 1 and a sample of population 2. For example, if a researcher wants to know, is the mean IQ of the classical music population different than the mean IQ of the non-classical music population, the researcher has to recruit a sample of people who listen to classical music and a sample of people who don't listen to classical music. And the researcher would have to record the IQs of both samples. And preferably, the two samples would be random. So the researcher would want to take a random sample of population 1 and a random sample of population 2. Like I said, the two samples should be randomly selected in this type of study. Sometimes they're not randomly selected, but they should be. So here's the diagram. A researcher is randomly selecting a sample from population 1 and collecting data from the sample, and the researcher is randomly selecting a sample from population 2 and collecting data from the sample. If I want to know if there's an IQ difference between these two populations, I would record the IQs of the people in sample 1 and the IQs of the people in sample 2. After the data is collected, the researcher has to calculate the mean of sample 1 and the mean of sample 2. In my IQ example, I would have to calculate the mean of all of the IQs that I recorded from sample 1, and I would have to calculate the mean of all of the IQs that I recorded from sample 2. The mean of sample 1 would estimate the mean of population 1, and the mean of sample 2 would estimate the mean of population 2. In other words, the mean of sample 1 would give me a rough idea of what the mean of population 1 equals, and the mean of sample 2 would give me a rough idea of what the mean of population 2 equals. So this is what I just said. In this type of study, the researcher would calculate the mean of sample 1 to estimate the mean of population 1, and the researcher would calculate the mean of sample 2 to estimate the mean of population 2. And here's the example I've been talking about. Imagine that I've randomly selected 5 people who listen to classical music. I've recorded their 5 IQs. and I randomly selected a sample of 5 people from the non-classical music population, and I recorded their 5 IQs. And I calculated the mean of sample 1 and the mean of sample 2. I calculated the mean of sample 1 by adding these 5 numbers and dividing by 5. And I calculated the mean of sample 2 by adding these 5 numbers and dividing by 5. X bar 1 is the mean of sample 1. X bar 2 is the mean of sample 2. So this sample mean right here estimates the mean IQ of the classical population, and this sample mean here estimates the mean IQ of the non-classical population. And in this type of study, it's important for both sampling distributions to be normal. In other words, it's important for the means of all possible samples from population 1 to be normal, and for the means of all possible samples from population 2 to be normal. So when I take my random sample from population 1 and I calculate the sample mean, and I take my random sample from population 2 and calculate the sample mean, this sample mean over here will be one of all possible samples that could be selected from population 1, and this sample mean here will be one of the means of all possible samples that could be selected from population 2. I want these possible samples to be normal, and these possible samples to also be normal. It's important for the two sampling distributions to be normal because if this sampling distribution is normal, then the mean of sample 1 is likely to be one of these accurate sample means in here, and it's a lot less likely to be something way too low down here or something way too high up here. I'm more likely to get an accurate sample mean than to highly underestimate or highly overestimate the mean of population 1. Also, if this sampling distribution is normal, the mean of sample 2 is likely to be one of these accurate sample means. I'm not likely to highly underestimate the mean of population 2 down here, or to highly overestimate the mean of population 2 way up here. And these two sampling distributions will be normal either if the two populations are normal, or if the two sample sizes are at least 30. So basically, in this type of study, I want either to know that these two populations are normal, and if they are normal, I can use any sample size. Or if I'm not sure whether the two populations are normal, I need to take at least 30 from population 1 and at least 30 from population 2. That way I know that the two sampling distributions are at least roughly normal. So like I said, you want to, in this type of study, when you're sampling from two populations and you're using a two-sample t-test, you want either the two populations to be normal, or you want to be using sample sizes of at least 30. And in most cases, you don't know if the two populations are normal, so your best bet is to just use at least 30 from sample 1 and at least 30 from sample 2. You want your two sample sizes to be at least 30. In this type of study, in which we're interested in whether the two population means are equal, these are the two competing possibilities. So in this type of study that we've been talking about, the null hypothesis says that the means of the two populations are equal. There's no difference between the population means. The alternative hypothesis says that the population means are not equal, and that there is a difference between the population means. In my IQ study, the null hypothesis would say that the mean IQ of the classical population is equal to the mean of the non-classical population. There's no difference between those two population means. The alternative hypothesis would say that there is a difference between the two population means. The alternative would say that the mean IQ of the classical population is different than the mean IQ of the non-classical population. Remember that the null hypothesis is the absence of something, and the alternative hypothesis is the presence of something. So in a study in which I'm interested in whether the two population means are equal, the null hypothesis is the possibility of no difference between the means of the two populations. The alternative hypothesis is the possibility of a difference between the means of the two populations. Just remember, absence, the possibility of the absence of something, and the possibility of the presence of something. And in this type of study, in which we're interested in whether the two population means are equal or not equal, this is how you would write out the hypotheses in symbols. So HO, which is a symbol for null hypothesis, says that the mean of population 1 is equal to the mean of population 2. And the alternative H1 says that the mean of population 1 is not equal to the mean of population 2. This is an equal sign and a not equal sign. So in my study on IQ, this would be the mean of the classical population, and this would be the mean of the non-classical population. And these are the two competing possibilities. So here's another example besides that IQ example. San Jose State University has, I think, this many students last time I checked, and Cal State East Bay has this many students. What if a person was doing a study in which he or she was interested in whether the mean commute distance of students at San Jose State is different than the mean commute distance of students at Cal State East Bay? Well, in this type of study, the person would randomly select a sample of San Jose State students and would randomly select a sample of East Bay students, and the person would calculate the mean commute distance of the San Jose State sample and the mean commute distance of the Cal State East Bay sample. After all of that data collection has been done, the person would want to come to a decision between these two hypotheses, or between these two possibilities. And in this person's study, the null would say that the mean commute distance of the San Jose State population is equal to the mean commute distance of the East Bay population. The two population means are equal. The alternative hypothesis would say that the mean commute distance of San Jose State is not equal to the mean commute distance of Cal State East Bay. So it's just equal population means and unequal population means. Basically, in any type of study in which you're interested in whether the mean of population 1 is equal to the mean of population 2, the null hypothesis says equal population means, and the alternative hypothesis says unequal population means. That's the way it always is in this type of study that we've been talking about. So, null hypothesis says that the population means are equal. The alternative hypothesis says that the population means are not equal. This just says how the population means would be calculated. In order to calculate the mean of this population, you would have to add up all of their values and divide by the number of population members. To get this mean of this population, you have to add up all of their values and divide by the number of population members. And the researcher in that study would actually would never know what this population mean equals or what this population mean equals, because the person would never have time to collect data from all members of the population. In order to actually calculate the mean of population 1, the person would have to collect data from all members of population 1. And in order to know the mean of population 2, the person would have to record all values from population 2. And the person would never have time to do that. So what the person has to do is calculate sample means. And the sample means estimate the two population means. So overall, what a person is doing in this study is calculating two sample means to estimate two population means, to be able to come to a decision about whether those two population means are equal or unequal. So this is just talking about the steps that we already went through. So let's now spend a little bit of time talking about the logic that's used in this type of study, and then later on we'll actually go over some of the calculations that are done. So the logic is, if the null hypothesis is true and the two population means are equal, the sample means are likely to be somewhat different because of chance, but they're not likely to be far apart. So if these two population means are actually 20 and 20, like they are here, then the means of the two samples should be close together, or at least fairly close together, because this sample mean will fall somewhere near 20, and this sample mean will also fall somewhere near 20, which means that these two sample means should be close together. You wouldn't be likely to get a sample mean, well, for example, this sample mean, you wouldn't be likely to get sample means of 5 and 45, let's say, because like I said, this one should fall somewhere near 20, this one should fall somewhere near 20. If the two population means happen to be the same number, then the two sample means should both fall around that number. So just remember, if the population means are equal, the sample means should be, or likely to be, close to equal. You aren't likely to get a large difference just by chance. Now, what if the alternative is true and the population means are not the same number? For example, what if the San Jose State average happens to be 16 minutes and the East Bay average happens to be 20 minutes? Well, if the population means are not equal, then you would expect a larger difference between the sample means, because if the population means are 4 apart, sample means should be about 4 apart. This sample mean should fall near 16 somewhere. This sample mean should fall near 20 somewhere. So, for example, the sample means might come out to 15 and 21, or maybe 17 and 22, or maybe 17 and 19. But overall, when H1 is true and the population means are not equal, the sample means are likely to have a bigger difference than when HO is true. So when you have equal population means, the sample means are likely to be close to equal with a small difference between them. When H1 is true and the population means are not equal, the sample means are likely to be further apart. So here's a diagram of what I've been talking about. Imagine that these are all of the commute distances in the San Jose State population, and the average is 20. The population mean is 20. These are all of the commute distances in the East Bay population, and the average, or mean, is 20. Both universities have a mean commute distance of 20, so the null is true because you have equal population means. Now, if this is actually the truth, and I go and I take my sample from San Jose State, and I take my sample from Cal State East Bay, this I'm likely to get two sample means that aren't that far apart, because well, I'm probably going to get the people I take from San Jose State will probably be somewhere around here, and their sample mean will be around 20, and the people that I get from East Bay will be probably around here somewhere, and their mean will be close to 20. For example, this sample mean might be, let's say, 12. This sample mean might be 26. But if the H1 is true and the population means are not the same, like they are here, then the sample means are likely to be further apart. For example, if San Jose State has a mean of 20 and East Bay has a mean of 40, then I'm likely to get a lot of people down near 20 from this university and a lot of people up near 40 from this university. This sample mean will probably be somewhere around 20. This sample mean will be somewhere around 40, and the two sample means will be much further apart. So the overall logic between, I'm going to skip ahead a little bit, sorry. Well, actually, before I skip ahead, let's actually summarize this one more time. When HO is true, and the population means are equal, the sample means are usually not exactly equal, but they're usually close to equal. There's usually only a small difference between them. They can end up being far apart, but it doesn't happen very often. It's not likely to happen. When the population means are not equal, you expect a bigger difference between the sample means. The sample means are likely to be further apart. And I'm going to skip ahead a little bit, sorry. And the idea is, if the sample means are far enough apart, if the sample means that the researcher calculates are far enough apart, the researcher will be convinced that H1 is true, that the population means are not equal, because if the researcher gets a big difference between the sample means, the researcher knows that that big of a difference isn't likely to happen when the population means are equal. When the population means are equal, the difference is likely to be small. So if the researcher gets a big difference between the sample means, the researcher thinks, well, this type of an outcome goes against what usually happens when HO is true. When HO is true, the sample means are usually close together. So since my outcome goes against what usually happens when HO is true, I'm going to reject HO and I'm going to conclude that there is a real difference between the population means. So, but what if the sample means end up being only a little bit apart? What if the sample means end up being really close? Well, then the researcher thinks that this outcome is consistent with what usually happens when HO is true. When HO is true, you expect to get a small difference. So, in that case, since the outcome is consistent with HO, you just give HO the benefit of the doubt. You just assume that HO is true. So we can see that if you get a big difference between the sample means, you reject the null hypothesis that the population means are equal because the outcome goes against what usually happens when HO is true. But if the sample means are close together, you fail to reject the null. You just assume that the population means are equal because that type of an outcome is consistent with HO. So here's a little bit of a summary. So now I'm going to skip over that part. Since I just told you that if the sample means are far enough apart, the researcher will be convinced that H1 is true and that there is a real difference between the population means. But how far apart do the sample means have to be in order to actually reject the null hypothesis of equal population means and decide that H1 is true? Well, in order to make that decision about whether the sample means are far enough apart to reject HO, you have to calculate a value called the T-score, and the T-score tells you if they're far enough apart. And let's go over the formula for a T-score. The top of the formula is just the mean of sample 1 minus the mean of sample 2, which is what the researcher is calculating. I told you that the researcher calculates the mean of sample 1 and the mean of sample 2. And in the top of the T-score formula, the researcher actually has to subtract the two sample means. Sample mean 1 minus sample mean 2. In order to calculate the t-score, the researcher also needs to calculate the standard deviations of the two samples. So the researcher has to calculate the standard deviation of the data from sample 1 and the standard deviation of the data from sample 2. And the two standard deviations have to actually be squared. You have to square this one and square this one. Squaring is just multiplying a value by itself. So the researcher calculates this standard deviation, multiplies it by itself, calculates this standard deviation, multiplies it by itself. And finally, the two sample sizes go into the formula. This is the number of people that are in sample 1 and the number of people in sample 2. So notice these subscripts 1 and 2. This means the mean of sample 1. This is the mean of sample 2. This is the standard deviation of sample 1, the standard deviation of sample 2. This is the size of sample 1, and this is the size of sample 2. And all of that gives you the t-score. The top part of the formula is called the sample mean difference because when you subtract the two sample means, the answer is the difference between the two sample means. The bottom of the t-score is called the estimated standard error of the sample mean difference. This is actually a value. The bottom of the t-score right here is actually a value that tells you how accurate the sample mean difference is likely to be. Remember how a standard error measures accuracy or how accurate you expect your outcome to be? In this case, the sample mean difference, the difference between the two sample means, is estimating the population mean difference. If these two sample means are estimating how far apart the population means are, and what this standard error tells you is how accurately the sample mean difference is estimating the population mean difference. If this standard error comes out to a big number, then that's telling you that the difference between the two sample means isn't likely to be very accurate. It's not giving you an accurate idea of how far apart the population means are. But if the standard error on the bottom is small, then that means that this sample mean difference is likely to be accurate. It's probably accurately telling you how far apart the population means actually are. That's just some extra details about the t-score. Let's move on. In order to actually use the t-score to reach a conclusion in this type of study, you have to compare the t-score to a cutoff point called the critical value. In the last lecture, I talked about how the critical value is the minimum point that the test statistic has to reach in order for the null to be rejected. If the test statistic reaches the critical value or higher, the null is rejected. And we said that the area that starts at the critical value and goes higher is called the rejection region. And the rejection region includes all of the outcomes that lead to the rejection of HO. We talked about that in the last video. In a two-sample t-test, the t-score that's calculated is called the test statistic. It's the test statistic, and what you do in a two-sample t-test is you look at whether the t-score reached the critical value and fell in the rejection region. If it did, you reject HO. You reject the null hypothesis of equal population means. Then you conclude that there is a real difference between the population means. If the t-score, the test statistic, falls below the critical value, you don't reject the null hypothesis. It's called a failure to reject HO, and you give the null the benefit of the doubt, which means you say there doesn't appear to be enough evidence that supports the idea that these populations are different from each other. In any type of hypothesis test, the test statistic is just the value that's compared to the critical value to make a decision about the null hypothesis. And in this type, in a two-sample t-test, the test statistic happens to be called a t-score. In other types of hypothesis tests, it has a different name, like sometimes it's called an f-score, sometimes it's called a z-score, but I just want you to know that the test statistic is the value that's calculated with the data and then compared to the critical value to make the decision about the null. And like I said, in a t-test, the test statistic is called a t-score. That's the name for it. So in a two-sample t-test, you calculate the t-score with the data, you compare it to the critical value, and then you make your decision about what conclusion to make in your study. Here we'll go through an example, a step-by-step example. So I'm doing a study in which I want to know if the mean IQ of the classical population is different than the mean IQ of the non-classical population. The question I'm interested in is whether these two population means are equal or if they're different. And I took my sample of 3 people from this population and my sample of 3 people from this population. I recorded these 3 IQs and these 3 IQs. I calculated the mean of sample 1 by adding these 3 and dividing by 3. I calculated the mean of sample 2 by adding these 3 and dividing by 3. I got my 2 sample means. I also got the standard deviations of the 2 samples. The letter S is a symbol for sample standard deviation. So I calculated this standard deviation with by plugging these values into a formula. I calculated this standard deviation by plugging these values into a formula. And let's just say that they both came out to 20. I think they actually did come out to 20, but I would have to double check my work. But let's just say that they did come out to 20 and 20. The 2 sample sizes are 3 and 3 because, well, I have 3 people here and 3 people here. That's where these sample sizes come from. These 6 numbers will go into the t-score formula to get our t-score. And to do the math, the first step would be just to subtract the 2 sample means on the top of the formula. Remember, the top of the formula is x bar 1 minus x bar 2. I subtract the mean of the classical sample by the mean of the non-classical sample, 120 minus 40. I have to plug the 2 standard deviations on the bottom. Remember, this is the standard deviation of sample 1, which is this. This is the standard deviation of sample 2, which is this. And I have to plug in my 2 sample sizes. The size of sample 1 right here, the size of sample 2 right here. And I have to square my 2 standard deviations. 20 times 20 is 400. 20 times 20 is also 400. So this squared is 400. This squared is 400. That's where the 400s came from. Next since both of these fractions have a 3 on the bottom, I can actually add the fractions. If the 2 fractions have the same denominator, I just add the 2 numerators. 400 plus 400 equals 800. And I just put that total of 800 above the 3. These 2 fractions get merged together right here. Remember, it's important to remember that when you add fractions, you don't add the denominators. So I don't add 3 plus 3. I just take the 3 and put it under here. Now I can divide the fraction under the square root sign. 800 divided by 3 is this right here. Now I just have one number under my square root sign. And Julian, now I just have one number under my square root sign. And now what I can do is just subtract on top. Oh, first, I want to make sure that you followed me when I said that when I got down to one number under the square root sign, I just hit the square root key, and I got my number on the bottom right here. Now I subtract the top numbers. 120 minus 140 equals negative 20. Now I just have a number on top and a number on the bottom, so I can divide. I just divide the top by the bottom. Negative 20 divided by 16.33 is negative 1.2. That's my t-score. It's my test statistic. I told you that every hypothesis test has a test statistic that's calculated based on the data, and it just happens to be in a t-test. The test statistic is called a t-score. Every hypothesis test has a test statistic that's calculated and then compared to the critical value later on, and it just happens to be in a t-test that's called a t-score. So my t-score is negative 1.2. And now what we have to do to make our decision about whether, in order to make our decision about whether these two population means are different from each other, we have to compare this t-score to a critical value and see whether this t-score reached the critical value. If this t-score that we calculated of negative 1.2 did reach the critical value, then what we would do is reject the null. In other words, we would reject the possibility that the population means are equal. We would say that these two populations do appear to be different from each other. If this t-score didn't reach the critical value, if it fell below the critical value, we would stick with the null hypothesis and say that there doesn't appear to be evidence to support a difference in IQ between these populations. That would be called failing to reject the null hypothesis. So our conclusion about whether we reject HO or fail to reject HO all depends on which side of the critical value our t-score fell on. We're going to have to actually go to a table and look up our critical value, and then after we look it up, we can actually compare this t-score to the critical value, see if it reached it. Before we look up the critical value, I want us to look at some t-scores of some other possible outcomes that we could have found, just to give you an idea of what the t-score represents. So here's 7 different possible outcomes that could have been found in the study. And each one would lead to its own t-score. What I want you to see here is that the two population means, if the two sample means come out to the same number, if they're equal, t is 0. If the mean of sample 1 is above the mean of sample 2, the t comes out to, if the mean of sample 1 is lower than the mean of sample 2, the t-score is negative. If the mean of sample 1 is higher than the mean of sample 2, the t-score is positive. Also, the further apart the two sample means are, the bigger the t-score gets. So here we have a big difference, a fairly big difference between the sample means, so t is a big negative number. Here we also have a pretty big difference going the other way, so t is a pretty big positive number. Now, if the two sample means are equal like they are here, that doesn't mean that the null hypothesis is true, because you have to remember that the null hypothesis is equal population means. It's not equal sample means. But if the two sample means end up being equal, the outcome is really consistent with the null hypothesis, because if the two sample means are equal, that suggests that the two population means could be equal. It's highly consistent with the null hypothesis of equal population means. The further apart the sample means are, the stronger and stronger evidence you have against that null hypothesis of equal population means. the further apart the sample means are, the more suspicious I would be that the population means aren't actually equal and that there actually is a difference between them. So I'm getting more convinced that HO is false if I get one of these outcomes. If I get one of these outcomes further out here, I'm more convinced that HO is false. If I get one of these outcomes out here, I'm also more convinced that HO is false, because a bigger difference between the sample means is a more convincing outcome. So it's more convincing that the population means are not equal after all. And notice here that when the sample means get further apart, t gets bigger. When they get further apart, when the mean of sample 1 gets further and further below the mean of sample 2 out here, you have a big difference like this. T is a big negative number. And if the difference is a big difference like this, t is a big positive number. So a big t-score convinces you that HO is false, because if you have a big t-score, like here, that means that the sample means are pretty far apart, and it means that you have a convincing outcome that HO is false. But what you have to do is you have to check to see whether the t-score is big enough to reject HO. It's only big enough if it reaches the critical value. And the critical value can be looked up in a table. It's called in a t-test, the table that you go to is called the t-table. You go to a column that says 0.95. Typically, the column that you go to is always 0.95. I'll explain where that comes from in just a few minutes. You also have to go to the right row in the table, which goes along with something called DF. There's a formula for DF in this type of study. What the DF really is it stands for something called degrees of freedom. And degrees of freedom is really just the name for the n-1 that we saw at the beginning of the semester. It's the name for that n-1 that's on the bottom of the sample standard deviation formula. And in this, so if you wanted to, you could just take off that n-1 and put df on the bottom instead, because they mean the same thing. Now, remember that in this, when you calculate the t-score, you're focusing. Remember that when you calculate the t-score, you have to calculate the both standard deviations of sample 1 and sample 2. The first standard deviation of sample 1 has its df of n-1. The other standard deviation of sample 2 has its df of n-1. You have to add those two df's together. So it's n-1 plus n-1 to get a total df of both standard deviations. And here's the formula that can be done to do that. It's the total sample size minus 2. So if my two sample sizes were 3 and 3, like they were in my example, I would add 3 plus 3, which would be 6, and subtract by 2, which would be 4. And that would give me my df, which in our example is 4. Since it's 4, I go to row 4. I go to my 0.95 column, because I told you that you always go to 0.95, typically. So our critical value is 2.776. That's our cutoff that our t-score needs to reach in our study. So Um, our critical value was, let's go back to see what it was, 2.776. Now we need to make a number line. This is the critical value of 2.776. This is actually the opposite of the critical value, which is negative 2.776. So here's the critical value from the table. Here's the opposite of the critical value. It's just the critical value with a negative sign in front. These marks off, when I mark off the negative critical value and the positive critical value, it gives us three different areas on this number line. This area above the positive critical value, or actually starting at the positive critical value and going up, is the positive rejection region. This area starting at the negative critical value and going down is the negative rejection region. This area is the non-rejection region. Now, with all this is saying right here is that if the null hypothesis is true and the two populations that you're sampling from are actually equal, then the t-score has a 0.95 chance of landing in this area and only a 0.025 chance of ending up out here and only a 0.025 chance of ending up here. Let's think about why that's true. Well, if the population means are equal, the sample means are likely to be close to equal. And that means that the t-score is likely to be near zero. The t-score only lands out here if it's a big negative number, and it only lands out here if it's a big positive number. And in order to end up in one of these two areas, in order to end up in one of these two red areas, you have to get two sample means that are pretty far apart to get a t-score out there. And that's not likely to happen when HO is true. So basically, when HO is true and the population means are actually equal, the sample means are likely to be close together. So T is likely to be around zero. And T is unlikely to end up way out here or way out here. And the logic tells you that if you get an outcome out here that's unlikely to happen when HO is true, you reject HO. You say that HO is false. The population means do have a real difference. If the outcome ends up out here, and it's an outcome that's unlikely to happen when HO is true, you also reject HO, because this is an unlikely to happen when HO is true. If the t-score lands in here, you have an outcome that's consistent with HO. It's likely this type of outcome is likely to happen when HO is true, so you don't reject it. You give it the benefit of the doubt. But so here, reject HO in this area, fail to reject HO in this area, reject HO in this area. But these two rejection regions lead to opposite conclusions. In this area, you would decide that the mean of population 1 is lower than the mean of population 2. If the t-score lands here, that's your conclusion. If the t-score lands out here, you reach the opposite conclusion, that the mean of population 1 is higher than the mean of population 2. So if the t-score lands here or here, you're rejecting HO, and you're deciding that the population means are different. It's just here, you decide that the difference goes in this direction, and out here you decide that the difference goes in the other direction. And so I showed you how in a two-sample t-test, you collect data from two samples, you calculate the t-score, you look up the critical values, you mark off the critical value on a number line, like we did here. You get these three areas, and then the conclusion just depends on which of the three areas the t-score falls in. Each area leads to its own conclusion, and that's a two-sample t-test. Here's just a little bit of review about what makes the t-score bigger and what causes the t-score to move up to the critical value. It becomes bigger when the sample means are far apart, like we said. It becomes bigger when the sample standard deviations are smaller. So actually, with smaller standard deviations also give you a bigger t-score. And also bigger sample sizes will help you get a bigger t-score. So if you want to reject the null hypothesis, you're better off with big sample sizes, because that brings your t-score up toward the critical value. But also we have to remember that if the sample means are equal, t will always be 0. So if the sample means are exactly equal, these last two things don't matter. T is always going to be 0. And I'll also send you an email pretty soon, like summarizing what we talked about and also giving any clarifications that are necessary. Thanks for watching.